Hello, everybody. So my name is Niamh Cahill, and I'm going to talk to you today about dealing with age errors in the statistical modeling of time-dependent data. So I think this session is called Becron and Beyond. I'm going to focus on the beyond part of that. So I want to think about and talk about how you deal with the uncertainties in the output that you get from age depth models when you're doing subsequent analysis. So what I want to do is talk through some slides briefly to give you some background and some context, and then I'll move on to something a little bit more practical. So as a very quick introduction, when we think about modeling time-dependent data, we don't usually have to worry about errors in the time or age variable because time is usually just known. But that's not the case when the time-dependent data is a reconstruction, where you have to reconstruct the time axis or the age axis. And so my research has focused a lot on the analysis of sea level reconstructions, where you use output from age depth models like Becron or Bacon to provide age estimates with uncertainty for the reconstruction. And so what I want to do is explore how you can deal with that uncertainty when it comes to doing statistical analysis, and to also look at the impact of not accounting for the uncertainty versus accounting for the uncertainty. So I want to just quickly talk about model specification first of all, as it gives some context. So I work in a Bayesian framework, but no matter what kind of framework you work in, you have to specify a model if you want to do any kind of statistical modeling. And so with a Bayesian model, the ingredients for the specification are usually the process model, which is usually where you have all the parameters that you're trying to estimate, the data model, which is where you make the assumptions about your data on the uncertainty in your data, and then the priors, which is where you can give some information that you might already know about the things that you're trying to estimate. And so what you do in a Bayesian framework is you combine the priors with the data model, which we sometimes call the likelihood, to give a posterior. And then the posterior tells you everything you need to know about the things that you're trying to estimate, which are usually the parameters that are in the process model. So there's a lot going on, but these are the main steps that you need to think about when you're specifying a Bayesian model. Okay, so just to give a little bit more detail on this, what is the process model? It relates to the expectation of what's underlying your data. So usually you have some observed data, it's usually noisy, has some uncertainties associated with it, and you want the truth that's underlying the data or the expectation of what's underlying the data. And so the process model is usually governed by the parameters that are controlling how you're defining the process, and then also some explanatory variables, maybe one or more explanatory variables. And so if we want to think about the way we would define this, it's the expected value of y, where y is the thing you're trying to model. And so often y in my case is relative sea level, for example. And so the process model would be giving us the expected value of y, which is just a function of a set of parameters and some explanatory variables. And often our x is just the age, which comes from, say, an age depth model in the sea level reconstruction example. And then we have the data model. This contains the assumptions about how the data are generated. It incorporates any uncertainty that you have in your data. And importantly, it links the data to the process that you've defined, which you're assuming is what's underlying your data. And so when we think about defining the data model, it's the uncertain data that we have, which we'll call y, which is going to be equal to the expected value of y as defined in our process model, plus some errors, which we have to assume a distribution for. And then the priors are going to contain any assumptions that we're willing to make about the parameters that we're trying to estimate. So you can use priors or think about priors as imposing constraints, and those constraints can be based on expert knowledge, based on just what you know about, say, the range of possible values that a parameter can take, based on previous studies. So whatever way you're specifying your priors, you can think about them as, or you can use them to put constraints on the things that you're trying to estimate where reasonable and if you can justify it. So I'm going to put this then into context with a specific type of model, which is one I'm sure many of you are familiar with, which is a linear regression model. And so you can set up a linear regression model in a Bayesian framework, and you can define the regression function as the process model. So in this case, when we have our process, which is our expected value of y, or the truth that we're trying to get at, which is a function of some parameters and some explanatory variable, for a simple linear regression, that function is just a linear function. And so our expected value of y is going to be a linear function of age, which is what we're going to be working with when we're thinking about developing models and using the output, say, from age depth models. So we have the expected value of y, which could be relative sea level, for example, as a linear function of age. And then the parameters of this process are alpha and beta, which we want to estimate. And then how do we link that to our observations? So we have some observations of y, which is going to be equal to the expected value of y plus some errors, because we know that our observations have some uncertainty associated with them, or some error associated with them, and they're going to vary away from what the expected value is. Those errors then have an assumed distribution, and when we are talking about simple linear regression, we assume that the errors have a normal distribution, and so this is where the data model part comes into it. So in this case, if you want to look at the notation, we'd have y is going to have or be a linear function of age plus error, and then the error is going to have a normal distribution centered on 0 with a standard deviation or a variance term. So I've written it in terms of the standard deviation here. And then this standard deviation is going to capture what we know about the uncertainty in our data. So this standard deviation can include measurement error if we have it, which we often do when we're thinking about, say, sea level reconstructions, and it can also capture any unobserved error that we might have as well. And then in terms of the priors, we might be able to make assumptions about alpha and beta in terms of the values or the plausible values that they might take. Or you can just assume that you don't know much about the parameters, and you can make priors what we call uninformative. In terms of the standard deviation, or the parameter that's telling us about the variation or the uncertainty, this has to be positive. So a standard deviation parameter has to be positive. So we have to, for example, make sure that that's a constraint that we have on our prior distribution for that parameter. So what am I interested in? I'm interested in what happens when X, or age in this case, has errors, because now we've looked at the example where Y had errors. So y is some expectation plus an error. But what happens if the same can be said for x, and x has errors? And so instead of the expected value of y being a linear function of age, which is the observed age that we have, what we want is the expected value of y to be a linear function of the true age. So actually what we want is our process, or in this case, a linear regression, to be a function of the truth, as opposed to a function of the uncertain or noisy observations. But we don't know the truth. So this is the problem. We didn't know the true y. We had to set up a model for it. We don't know the true age either. So we have to account for that. But luckily, especially when we're working in a Bayesian framework, it can be quite straightforward to think about how you might deal with this. So we can use what we call an errors and variables approach. And what we can do is, again, assume that we have this x, which is our observation, is going to be equal to some expected x, which is our truth, plus an error. And again, you can make an assumption about the errors. A simplified assumption is to assume that the errors are normal. And then you can set up the model in a similar way. So we're not going to have a regression function here. What we're going to say is just age is equal to the true age plus an error. And the error has a normal distribution centered on 0 with, again, a standard deviation that's going to capture the uncertainty that we have in the age now this time. So what we have now then is a model for our age variable. And what we need is an estimate of the truth. And so we can put a prior on it. It's something that we don't know when we're working in a Bayesian framework. We can put prior distributions on the things that we don't know. They're just assumed to be parameters that you need to estimate. And so we can put a prior on this true age, and we can get an estimate of it, and then we can use it in our regression model. So when you think about constraints for this, you can put a prior on the age within some plausible range. And so depending on the range of ages that you're working with, there's probably a plausible range, or you can put bounds on it in some way that you know it's not going to go beyond certain values. And so when you set this up in this way, this is called an errors and variables model, okay? And you can extend these models beyond simple linear regression. So what I want to do is look at this web application that I've created, which will allow us to explore the impact of including or excluding the age uncertainty in the linear regression. And then I just want to briefly talk you through some OR code that I've created that will allow you to run the simple regression models and also the more complex Gaussian process regression models, also including and excluding the age uncertainty. Okay, so let's look at the web application. So I'm going to open this in a new tab. So you should be able to click the link and you should be able to open this app here. And so what this does is it will allow you to explore the errors and variables idea with simple linear regression. So what you can do is you can simulate data that has, the simulation is coming from a model that has age uncertainty. So the true underlying model has accounted for the fact that you have age uncertainty, and we know what the truth is, and then we can fit our models and compare to the truth. So we're simulating data with age uncertainty, and you can specify the intercept or the slope parameters. And then you can also specify the error in years, and then you can simulate your data set. So let's look at, say, choosing n equals 20. We'll make the slope 1. I'm going to choose the error to be, let's say, 100. So in this case, each data point will have that error, and then you can simulate the data. And so what we have here is the simulated data, which is shown with the points and then the boxes around it. So the simulated data is the error prone data, okay? And I've set it up such that it has error in Y and error in age, because that's what I typically deal with when I'm modeling sea level reconstruction data with errors in both axes. So we have errors associated with each of these points, and then the green line is the truth. It's basically the true process that generated these data, and the true process was a function of the true ages, which I know because I simulated the data, but in practice we wouldn't actually know. So I'm trying to, when I fit my regression models, get as close to the truth as possible. And when you can show the results then, and when you show the results, it will show you the results of fitting the simple linear regression and then the errors and variables regression. So accounting for and not accounting for the age error. So if you click show results, so you can see here, this is the model results with and without modeling age or error in age. The red is the errors and variables, and the blue is just without the errors and variables. So the red will account for the error in the age direction. The blue won't. Both models account for the error in the Y direction because we're mostly used to doing that anyway. And then here, what you have is, this is the posterior distribution for the slope parameter, which is telling you about, which will give you the rate of change in, for example, Y per year, or for the data that I usually work with, we're looking for the rate of change in sea level per year. So this gives you the posterior distribution for that parameter because it's the one we're usually most interested in. And the density plots are shown here, and then the horizontal lines that you see here. So you have the point giving you the point estimate, and then you have say a 68% uncertainty interval, and then a 95% uncertainty interval. So what we want ideally is for the truth, which is the green dashed line, again, to be within the 95% uncertainty interval or the 95% credible intervals when it comes to what our model is producing. So that's what we're looking for. So for this simulation, both models do pretty well. There's not much of a distinction between both of them. And so you can simulate another data set. Again, that doesn't look very different. You can simulate another data set. So you can simulate various data sets, and then you can show the results and you can see the impact. And so when we have an error of 50 years in this example, where the age spans like 0 to 2000 years, you can see that you're getting similar results for both models. But you can simulate lots of other data sets and see how often that's the case. Now we can up the age error. So let's up to 200 now, for example, and then simulate again. So the data will be simulated and then it will fit. And now what you're seeing, so if you look now at the red line compared to the green line, which is the truth, the red line is closer to the green line here than the blue line is. And so that's the errors and variables model. And you can see here when you look at the estimates, the posterior distributions and the estimates, the truth is, the estimate is further away from the truth in the simple linear regression model compared to the errors and variables where you get the estimate much closer to the truth. In this case, it's still within the 95% uncertainty interval, so it's still not doing too bad. And so what's happening here practically is that what you're going to do is you might underestimate the slope in the simple linear regression model. So the truth was 1, your estimate is going to be about 0.85. So you get an underestimate of the rate of change there. And it could work the other way. You could also get an overestimate. So you're biasing your estimate of your rate of change by not accounting for the age errors, which is why we want to account for them when we're thinking about modeling. Let's up it again just to have an example. So if we up to 400 years, let's simulate that data. So it'll just take a minute and then it'll simulate the data. And now you can see again, the red line is closer to the green line and the slope is being underestimated again when you just use a simple linear regression model compared to using the errors and variables model. So here it's actually outside the 95% credible interval, whereas here it's not as close to the estimate is still lower than the truth, but it's still within the 95% credible interval. And you can just keep playing around with that. And then what I also want to do is, if you're interested in kind of going a little bit further with this, I have some R code up on GitHub that will allow you to fit these models. So you can fit the regression models and you can get the output, and you can also fit the more complicated Gaussian process models, and you can do it with and without accounting for the error. And you can see the impact that it has, again, on simulated data, but you can also include your own data if you want to. So the R code, if you click on the link here, it'll take you to GitHub. So what you can do when you get to the GitHub page, it has a README here, so have a look at that. It's just telling you that you need to install JAGs, and I have a link here for where you can install JAGs. That's what's used to fit the Bayesian models. And then you can download the repo and then open the or.proj file in RStudio, and that will have you in the directory where everything should work for you, and then you can just open the main script and to run the models. Okay, so once you open the project, you'll be brought into the project directory, and then you can just open the main script, and then you can start to work through running the code in this script. It's all commented, and it should just work, hopefully, without any too many issues. So if you load all here, this line of code, that's just loading all the functions that are needed. Okay, so once you do that, you won't have to worry about trying to access any of the functions. Okay, so this load all will also load a set of the libraries for the OR packages that are required, but what you need to do is have them installed. So make sure you have the list of packages installed that are up on GitHub. So this function here will simulate some data. Okay, similar to what you saw in the app there. So you can choose the number of data points, you can choose alpha, you can choose beta, and you can choose the age error. Okay, so that's similar to the application. And then you can plot that. Now, if you plot it and you give it alpha and beta, it will include the true line on the plot. And if you don't give it alpha and beta, it will just plot the data. So you can plot there and you can see you have the simulated data with the truth here given in green. And if you didn't include the alpha and the beta, it would just give you the line without or would just give you the data without the true line. And then you can run the models. So here, this will run the model. When you specify the model equals reg model, it will just run the simple linear regression model for you. And that will run very quickly. And then you can just get the estimates of the slope So here, and the intercept actually. So by running this, you just get the alpha, and then you get the 95% uncertainty interval. So you get the lower and the upper, and then you get the beta and the lower and the upper. And you can plot that, and you can compare it to the truth. Now here it has the plot with the uncertainty interval. So this is a 95% uncertainty interval for the regression line. And so you can see how it deviates from the truth there. And then you can fit the errors and variables version. So if you run through this, you should be able to fit the errors and variables version. The model here is EIV reg model. So once you specify that, it will do the errors and variables for you. Again, you can get the estimates here. The beta is slightly larger than it was. The estimate is larger than it was when we did just the simple linear regression. And then you can plot that. And so you can see the true line is within the 95% credible interval here, where it was outside of it here. So we're getting closer to the truth when we fit the errors and variables. And then you can compare both if you want to. So when you plot the results and you give it the first model and the second model, it'll just do a comparison of both for you. So you can see that the red is closer to the truth than the kind of bluey, the kind of blue shaded region there. Okay, so that's how you do, or that's how you can run the simple linear regression errors and variables, and you can give it your own data. So this is based on simulated data, and it's using the simulated data to kind of as proof of concept. But if you give it the data in this format, so if you give it a data set where you have age error, Y and Y error with these names, then you can actually run it on your own data if you want to. Okay, so it'll work if you just create that, but it's your own data set, not the simulated data set. This will work. And then you can also do the Gaussian process version. Okay, so I hope you find that helpful. I hope you get a chance to maybe run through the code, and then I'll see you on the 19th if you have any questions or want to ask me anything about any of this.